towards the center of the circle. And that would be the simplest case of orbital motion, where you just had something moving around a circle in uniform circular motion. And so we can use that as an analogy for how orbits work. The simplest kind of orbit, a circular orbit, well, you could have a ball held in uniform circular motion by the tension of a string. The string would be pulling inwards on the ball, and it would be moving in uniform circular motion around the circle. If the string snapped, the ball would fly away. The moon, well, let's take Earth going around the sun. It's almost uniform circular motion. So the force on Earth is towards the center of the circle, or more precisely, it's towards the sun always while it's moving in its elliptic orbit around the sun. And so you can think of gravity as playing the same role as the string. In other words, the force of gravity is what's causing Earth to follow a curved path instead of just flying off in a straight line. Gravity is playing the role of the string. Now, you asked about energy conservation and all that sort of thing applied here. A more interesting case there is elliptical motion, the motion of the planet moving on an ellipse. In that case, so what about when you've got something orbiting, you've got two kinds of energy. You have kinetic energy of the orbiting body, and you've got potential energy, gravitational potential energy. Gravitational potential energy, is it bigger or smaller when you bring bodies further away from one another? Does that raise their gravitational potential energy or lower their gravitational?
Lower.
You bet not. That's backwards. Here, if I raise this object further from the center of the Earth, I have to do work on it to do that. It doesn't want to do that. So I'm raising its gravitational potential energy. So when things are further apart, they have more gravitational potential energy. When they're closer together, they have less gravitational potential energy.
And then the speed is further apart than if you increase orbital speed, then that means that
yeah, I'll do that right here. I'll do that right
kinetic
here.
energy goes
Okay,
up,
consider here's a planet going around the sun. Okay? When it is far from the sun versus close to the sun. Okay, so here I'll go from when it's closest to the sun, it's moving away from the sun. As it's moving away from the sun, what is happening to the gravitational potential energy? Is it going up or going down?
Going up.
Going up. What is happening to the kinetic energy?
Down.
Going down. How do we understand that?
No.
What about the total energy? If I add the gravitational potential energy plus the kinetic energy, how does that vary around the orbit, or does it vary?
It stays
It stays the same, right? The magic word, it's a C-O... Conservation of energy, right? The total orbital energy, potential energy plus kinetic energy, is constant, it's conserved. So if you're going further away from the sun, the potential energy is increasing, and to compensate, the kinetic energy decreases at the same rate that the potential energy is increasing. And vice versa when you're coming towards the sun. When you're coming towards the sun, the potential energy is going down, the kinetic energy is increasing to compensate so that the total energy stays rock solid, constant. So this is one way to understand why planets go faster when they're closer to the sun and slower when they're further from the sun. When they're closer to the sun, they have less gravitational potential energy and more kinetic energy, and vice versa. When they're far from the sun, they have more gravitational potential energy and less kinetic energy. The sum stays constant, but they can be transformed into one another. Energy conservation says the total energy is constant. You can't create or destroy energy, but energy can be transformed from one form to another. And if you transform kinetic energy into potential energy, basically the planet loses just as much kinetic energy as it gains potential energy, and vice versa at any point as it's moving around the orbit. Yes?
For the Kelvin scale, we're just going to know freezing, boiling, 0 Kelvin, that's it.
Yeah, 0 Kelvin. What do you call 0 Kelvin?
So
That's absolute zero.
Absolute zero, and then
yeah, and then
freeze to 7 degrees.
how big are Kelvin degrees compared to Celsius degrees? What I mean is, if I change the temperature by 1 Celsius, how many Kelvin has the temperature changed by?
That's a good question. That's really a question.
Oh, yeah. There's a really easy answer to that.
1.
Yes. A Kelvin degree is the same as a Celsius degree. It's just, they just have different 0 points. They just have different 0 points. Absolute zero Kelvin is absolute 0. That's minus 273 Celsius. So the Kelvin and Celsius scales are the same, except they're shifted by 273 degrees with respect to one another.
You get it in Fahrenheit too?
No.
Alright, good.
Nobody uses Fahrenheit except
That's American.
people in here in America watching weather forecasts and sticking thermometers in themselves. Nobody else uses Fahrenheit. It's a silly scale. I mean, it's fine, but you know, it's old-fashioned. Fahrenheit, when he invented the scale, he wanted 0 Fahrenheit to be the coldest temperature achievable by the technology at the time, and 100 Fahrenheit to be human body temperature. Well, you know, the coldest you could achieve by the technology at the time is not the coldest you could ever achieve. So that was a bit of an odd choice because technology improves, you can get colder temperatures. And of course, human body temperature is close to 100 Fahrenheit, but it's more like 90 and something. Even the canonical 98.6, that's been revised, we now know. Not everybody's 98.6 Fahrenheit. Yes?
Can you go over the escape speed?
Sure. So escape speed is the speed required for something to fly away and never return.
Okay.
So, in other words, imagine take the air off of Earth's surface because that would get in the way. Question is, how fast would you have to launch something? How fast would you have to throw something upwards such that it would certainly slow down as it moved away from Earth because gravity would be pulling back on it, it would slow down. But if something's moving fast enough, it would fly forever. It would never slow down to 0 speed if it was moving fast enough. Escape speed is the borderline where very, very far away, an infinite time, basically infinitely far away, an infinite time later, the thing would slow down to 0 speed. It's kind of the borderline where it would fly away forever, but in the limit of flying away for literally forever, it would finally slow down to 0 speed. If I launch something at less than the escape speed, what eventually happens to it?
Right.
It comes back. If it's going less than the escape speed, then it eventually stops for a moment, and then if it were launched straight up, and then it would start falling back to Earth again. If I launch it faster than escape speed, it never stops. It would fly away forever. For Earth, escape speed is about 25,000 miles per hour, or about 40,000 kilometers per hour. So that's, you know, it's fast, just what it comes down to.
Can you repeat that again, the numbers?
It's like 25,000 miles per hour for Earth, 40,000 kilometers per hour. That's for Earth. For Jupiter, it's higher because Jupiter has stronger gravity. For the Moon, it's lower because the Moon has weaker gravity. So it took, it's a lot easier to launch a rocket from the Moon than from the Earth. The Apollo astronauts didn't need nearly as strong a booster to get them off of the Moon as it took to get them off of the Earth because the Moon has much weaker gravity and therefore much smaller escape speed. So if we want to send probes to distant planets, we basically need to launch something from Earth orbit or from the ground such that it reaches escape speed so that the thing will fly off into the solar system. Now, it still is gravitationally bound to the sun. We've only got, I think, 2 probes, the Voyager probes, that are moving fast. No, then there were 2 Pioneer probes before that, moving fast enough to just fly away forever from the sun. And I think the one that flew by Pluto also is moving past solar escape speed. Escape speed depends on where you are. The further away you are from Earth, the lower the escape speed is from that location. Okay. Any other questions about that? Okay, next question.
talk about planetesimals?
Planetesimals. So, first of all, how do planets grow from the disk, the protoplanetary disk surrounding the sun? Can the hydrogen and helium gas directly form a planet? No. No. Hydrogen and helium gas doesn't directly form a planet. At least we don't, at least it typically wouldn't. There are some ideas that under the right conditions it could. Planet formation is seeded by the collisions and sticking together of tiny little dust steps within the protoplanetary disk. So, condensation of rocks, metals, and if you're in the right location, ices into little specks of dust is how planet formation begins. Little microscopic dust specks can collide with one another and stick to make slightly bigger, but still microscopic dust specks. But that process continues. And after a while, they're not microscopic anymore. They be little pebble sizes, and little boulder sizes, and big boulder sizes, and house sized, and so on and so forth. Planetesimals are building blocks of planets that form by accretion. Planets form by the accretion of planetesimals. And there's no hard and fast, eventually if a planetesimal gets big enough, you start calling it a protoplanet. Once they're planet size, they're protoplanets. They're not yet planets because if there's still a lot of protoplanets and planetesimals around, they're going to keep on growing. There's no hard and fast division between protoplanet and planetesimal, or you can just think of a protoplanet as a very large planetesimal. But in other words, the planetesimals were the building blocks of the planets. They formed by accretion of the dust specks in the solar nebula. So, are there any planetesimals left in the solar system today? Comets and asteroids are leftover planetesimals that never became part of planets. That's how we explain their presence, leftover planetesimals.
Does the cross line just like separate Jovian and terrestrial planets?
It separates where they can form, yes. So, first of all, what is the frost line? Did you define what the frost line is?
Just a bunch of like comets, right? Like asteroids?
No, it's a distance from the sun. It's a distance from the forming sun. What's true outside, beyond the frost line, compared to inside the frost line? Hydrogen compounds can condense and solidify outside the frost line where it's colder than it is inside the frost line. So hydrogen compounds, not hydrogen and helium, but hydrogen compounds, in particular, the most common ones are water, methane, and ammonia. They could condense to form solids outside the frost line, beyond the frost line. And so in the outer solar system, you could have rocks and metals and ices in solid form. Inside the frost line, it was too warm for ices to solidify. Rocks and metals could still solidify because they have higher condensation temperatures. And so, big picture is that there was only solid materials available for planet building. Hydrogen and helium gas everywhere was the most abundant stuff, but the gas isn't available for planet building. So beyond the frost line, the ices meant you had solid ices meant you had additional material available for planet building compared to inside the frost line. So the Jovian planet's cores grew faster to larger masses than the terrestrial planets did because the Jovian planets had ices and rocks and metals to be built from, whereas the terrestrials only had rocks and metals to be built from. So the Jovian planets were able to get larger initially as bodies made of ices, which wouldn't be still solidified when they were part of the protoplanet because it would be too warm then. But in other words, their cores could get large enough, their cores could get large fast compared to in the inner solar system. And when their cores reached about 15 Earth masses, then their gravity was strong enough to start pulling in hydrogen and helium, which is why the Jovian planets have a lot of hydrogen and helium. They got big enough to attract hydrogen and helium gas directly via their gravity. And hydrogen and helium gas was by far the most abundant material. So once you can tap into that, you can grow very rapidly. That's why Jupiter and Saturn are so large. They can tap into the abundant supply of hydrogen and helium gas and add it to themselves. Earth's gravity was never strong enough to pull in and retain hydrogen and helium gas. So we never grew like a Jovian planet did, which is good because if we did, we wouldn't be having this conversation. Yes?
So, it's kind of confusing, so the Jovian planets are bigger than the terrestrial planets?
Much larger.
But they're
yeah.
not as, they have lower densities?
They have lower densities, yeah, because remember that density is mass divided by volume. And so Jupiter has about 300 times the mass of Earth, but
Saturn.
way more than 300 times the volume. Jupiter has about something like 1,500 times the volume of Earth and 300 times the mass of Earth. So
The
its
diameter is
density-
10 times, right?
its diameter is 10 times, yeah, about.
And then,
About 10 times,
Neptune
well, like
and
11
Uranus is
times.
4 and 15, right? 4 diameter, 15. and-
4 diameter, 15 masses roughly, yep. Yep, sounds like you got that down.
Oh, I've been all night, all
So the
day.
Jovian
yeah,
planets
Rapid
are
pump happening.
solid on the inside and they just have a lot of gas on the outside?
They have cores which are rocky, which are made of rocks and metals, but they're under really high pressure. And so